Module 4, Lesson 34, Writing and Graphing Inequalities in Real-World Problems, our last learning target for this module. I can use substitution to determine whether a given value makes an equation or inequality true. So we stick the number in and see what happens. I can write and solve equations and inequalities involving real-world problems. So here we go, looking at some real-world problems, and really fun in this lesson. We are going to be graphing the inequalities. We're going to put them on number lines. I can show and explain that inequalities in the form x is less than c and x is greater than c, where x is a variable and c is a fixed number, have infinitely many solutions when x comes from a set of rational numbers. So if we are looking at rational numbers, all of the numbers that can be expressed as ratios, then these inequalities have infinite solutions. I can represent real-life situations by writing and graphing inequalities. Don't worry about this first I can statement. As we start to look at it, it will start to make more sense. Here we go, real-life situation. Caleb has at least $5. We need to stop and think about what does that mean? How much money could Caleb have? Could he have $5? Well, it says he has at least that. That means $5 is the least amount of money he has in his pocket. So I could say that he will be equal to $5. Could I say that he has less than $5? Well, it says the least amount that he has is $5, so he can't have less than 5. What about more than 5? Could he have $6, $10, $12, $1,000, $1 billion? It says the least amount he has is $5, but it could be more than 5. So he could have $5, $5 and a penny, $5.90, $6, $7, $8, $9. More simply, he could have 5 or any amount greater than 5. So his money could be greater than or equal to 5. How would we show this as an inequality? His money is greater than or equal to 5. And of course we have a table here to put it on. How would we show this on the number line? How would we graph this as a solution? I need to show that he has $5 or more. So I'm going to start at the 5. I'm going to put a circle. If you have colors, you can put it right on the number line. I usually like to go right above the number line. I am going to fill in the little circle here for 5. If I fill in the circle, that means equal to. So he could have $5 and he could have anything more than $5. So I need to show that 5 is a solution and everything to the right of 5 is a solution. So because we want to include 5 in the solution, I'm going to fill in the circle. And then I'm going to do an arrow to the right and show that all the numbers 5 and greater are part of the solution. Now this is where that infinitely many solutions comes from. If we go greater than 5, we have a never-ending number of numbers that is greater than 5, an infinite number of solutions. So how does this statement about Tarek, how is that different than what Caleb has? Well, it says Caleb has at least 5. Tarek has more than 5. So could Tarek have exactly $5 in his pocket? Well, it says he has more than 5, so this is not true. He has to have more than 5. Tarek has more than 5. He cannot have exactly 5, where Caleb might have had exactly $5. How would I write this as an inequality? Tarek has more than $5. His amount of money is greater than 5. How would I graph the solution? 5 is not a possible, but I'm going to start my line there. Some students would say, oh, you need to start with 6. And my only question is, what about all the numbers between 5 and 6? Could he have $5.01? Would that be more than $5? So as we use the graphs, these number lines, we'll start at 5, but we won't fill it in because he's not equal to 5. What we will do is include everything greater than 5. When we graph the inequality for Tarek, we still want to circle on the 5, but this time it will not be solid to show that 5 is not included. 5 is not part of the solution, but everything to the right of 5 is. When it says someone has at most, what does that mean? It means the very most that they have. The very most that it is possible for Vanessa to have is $5. She can't have more than 5. So Vanessa could have $5, but no more than 5. She could have less than $5. 4, 3, 2, 1, $2.50, $4.50, $0. She could even have a negative amount of money if she owes someone money. How would I write that as an inequality? Pause and do that. Compare your work to mine. Vanessa is less than or equal to 5. Pause. How would you put this on the graph, on the number line? Pause. Give it a try. It says equal to, so I'll start at 5 and I'll fill in the circle. But it says that I am less than 5, so I'm headed to the left. Vanessa has less than or equal to 5. The most that she has is 5. Pause and go ahead and think about Li Chin and write your inequality and draw the graph. All right. Is Li Chin's the same as Vanessa's? Well, Li Chin says less than 5, where Vanessa has at most 5. Li Chin could not have $5, but Vanessa could. So I would say that Li Chin is going to be less than 5, which is hopefully what you said. They're similar, but not exactly the same. Li Chin cannot have $5 exactly. So the circle on his graph has to be open, even though it still goes to the left. Kelly works for quick oil change. If customers have to wait longer than 20 minutes for the oil change, the company does not charge for the service. The fastest oil change that Kelly has ever done took 6 minutes. Show the possible customer wait times in which the company could charge the customer. Pause and think for a moment. How is this example different from the problems in example 1? Hopefully you recognize that this one is giving a range of possible values. He can't change the oil in less amount of time than his fastest. 6 is the fastest he's ever done. I certainly can't have negative numbers. I can't say that he finished at 2 minutes before you got there, which is negative 2 minutes. But I also know that if he takes longer than 20 minutes, that the company won't charge the customer. Now, is it possible that in the future this 6 could change? Could it become 5.5 or 4? Absolutely. But based off of the information we have right now in this problem, 6 minutes is the fastest that he has ever done an oil change. So the company is going to be able to charge money in a range. Instead of an infinite amount, anything greater than 6 minutes, they'll get paid. It has a cutoff. And I can't say anything less than 20 minutes the company gets paid, because we know that he has never done an oil change faster than 6 minutes. Somehow I need to show that this middle section is the range in which the company can charge the customer. So let's start with the first bit of information. The second sentence tells us the fastest that Kelly has ever done took 6 minutes. So 6 minutes is one end of the range. Oh, sorry, I'm on the third sentence. Second sentence. customers have to wait longer than 20 minutes for the oil change, the company does not charge. So 20 is one end of the range. If it's more than 20, the company doesn't get paid. 20 minutes and 1 second, company doesn't get paid. So the oil change must take 20 minutes or less. So on the number line, I would show 20 minutes or less this way. Now, the other piece of information, which I already gave to you, the fastest oil change Kelly has ever done took 6 minutes. So the time for Kelly to conduct an oil change is 6 minutes or more. And I would show that on the number line by filling in the circle and shading to the right. So showing these together, I have to combine these two graphs. So I'm going to drag, see if it'll drag here. I'm going to drag them together and combine them. Of course, it left my, oh, boy, it's just not playing nice, but that's okay. There we go. There's 6. All right. Drag my point up there. Not that. There we go. So if I combine the two lines, I can see that I have one end of getting paid is at 20, and the other end of getting paid is at 6. And anything outside of those, the company isn't getting paid. Remember, I always have a student who says, well, what if he goes faster than 6 minutes? Okay, well then this is going to move on the left-hand side. But right now, as of this very minute, the company is going to get paid between 6 minutes and 20 minutes. The circles should be solid because we're including those times. It's 20 minutes or less equal to 20 is part of the solution. 6 minutes is the fastest he's ever done. So it's filled in. Example 3. Grenars has been mowing lawns to save money for a concert. Grenars will need to work for at least 6 hours to save enough money, but he must work fewer than 16 hours this week. So he needs to work at least 6 hours, but he can't work more than 16. He has a range. Write an inequality to represent the situation and then graph the solution. So if we were to show he's working at least 6 hours, at least tells us he must work 6 or more, the least. So his amount of work is going to be greater than or equal to 6. And on our number line, we should be thinking, oh, I can fill in the circle at 6, and I know that I'm headed to the right. And I already drew the graph. Now, to show that he has to work fewer than 16 hours. Now, it doesn't say he can work 16 hours. It says fewer. I have to be less than 16. So I would write an inequality that the work is less than 16. And about now, your brain is like, ooh, ooh, ooh. So I know that I'm going to draw an open circle and draw to the left. And then I can combine the two circles. Sorry, the two lines. If my circle would actually move with me here, which it doesn't want to do. There we go. So now I can combine the two lines, and I can see that I have a line that starts equal to 6 and ends less than 16. Now, one other kind of add-on thing here, we could write it as x is less than 16, the amount of work, but it is also greater than or equal to 6. So I have combined the two inequalities into a single statement. X is somewhere in here, less than 16, but greater than or equal to 6. Exercises. Write an inequality to represent each situation, then graph the solution. Blayton is at most 2 meters above sea level. The most he could be is 2 meters. He could be less than 2 meters. He could be 2 meters, but he can't be more. At most includes the 2. So he is, at most, Blayton is less than or equal to 2 meters, or I could think of it this way, 2 meters is greater than or equal to Blayton. So I have equal to, so I'll fill in the circle, and Blayton is somewhere to the left of this. The most he's at is here. Exercise 2. Write an inequality to represent each situation, then graph the solution. Edith must read for a minimum of 20 minutes. Minimum means at least. The least amount of reading is 20 minutes. Anything more than 20 would be okay. Minimum of 20 minutes. So as I think about that on my graph, she could read 20 minutes and she could be okay. And she could read anything more than 20 minutes and she could be okay. So Edith's reading must be greater than or equal to 20 minutes. Or I could say that 20 minutes is less than or equal to the amount of reading that Edith must do. Travis milks his cows each morning. He has never gotten fewer than 3 gallons of milk. However, he always gets fewer than 9 gallons. So 3 is the very least that he gets. But I also know that it's always less than 9. He's never gotten fewer than 3 gallons, but when I read that, that tells me that he could be at exactly 3. So the amount of milk could be equal to 3, but it could also be greater than 3. But I also know that it's always fewer than 9. That doesn't include 9. It says fewer than 9. So the milk is always less than 9. So if I take these two statements here and kind of combine them together, the milk is going to be never fewer than 3. Ooh, I need to combine the equal sign and the less than sign. And we've never gotten more than 9 gallons, which is another way of saying we've always had fewer than 9 gallons. The milk is always less than 9 gallons. The milk has always been greater than or equal to 3 gallons. Putting that on the graph here, greater than or equal to 3, less than 9, and our range is there. Exercises 4 and 5. Write an inequality to represent each situation, then graph the solution. Rita can make 8 cakes for a bakery each day. So far, she has orders for more than 32 cakes. Right now, Rita needs more than 4 days to make all 32 cakes. Let's see. So I'm going to use this first number line for this problem right now. She has orders for more than 32 cakes. Right now, Rita needs more than 4 days. She's going to need more than 4 days. Her number of days are greater than 4. There's the first part of the problem. Rita must have all the orders placed right now done in 7 days or fewer. Oh, so she doesn't just have more than 4 days, she's also got a deadline, a time she has to have it finished by. So she's going to need more than 4 days, but she's also going to need less than 7 days. So more than 4, but less than 7. Oh, it says 7 days or fewer. That means I can include the 7. That's a whole extra day there. So the number of days are greater than 4, but they are less than or equal to 7. And it's okay if you're not writing them all in one statement like that. Just express it as the days will be greater than 4 and the days will be less than or equal to 7. If you feel comfortable combining them into one statement, go ahead. Exercise 6. Write an inequality to represent each situation, then graph the solution. Casey has been mowing lawns to save up money for a concert. He earns $15 per hour and needs at least $90 to go to the concert. How many hours should he mow? Well, if he mows 3 hours, that's $45. If he mows 4 hours, that's $60. And 5 hours is $75. And 6 hours is $90. It says he needs at least 90. So 3, 4, and 5 aren't going to get the job done. At least means he could have exactly $90, but he would probably be okay with a little bit more money. So he needs to mow, his hours need to be greater than or equal to 6. Because it says at least. He could mow longer and have more money. Rachel can make 8 cakes for a bakery each day. So far she has, this looks like somehow I've got an extra copy in there. I'll have to get rid of that. Ranger saves $70 each week. He needs to save at least $2,800 to go on a trip to Europe. So he saves 70 each week. He's shooting for 28. How many weeks will he need to save? Well, boy, those are some big numbers there. Maybe I'll kind of think of it this way. I'll do 25 times 7. 25 times 7, and then I'll multiply by 10. 4 25s is 100, and 3 more gets me 175, and then multiply by 10. Well, that's not going to get him on the trip now, is it? 70 times 30 is $2,100. We're getting a little bit closer, but still not on the trip. What about 40 times 70? That would get us $2,800. It says he needs at least $2,800. So the very least he could save is for 40 weeks. If he saves for longer, he can have more money. At least. So his number of weeks has to be greater than or equal to 40, the least amount. Clara has less than $75. She wants to buy 3 pairs of shoes. What price shoes can Clara afford if all the shoes are the same price? So she has to spend less than $70. She has less than 75. Well, if I do 3 pairs at $25, and my brain went to 25 because I know that 3 25s make 75. If she does $25, she's exactly $75. So 25 is not going to work. A mistake that students make at this point is say, oh, it must be 24. Well, what about all these amounts, these dollar amounts between 24? Could she get 3 pairs of shoes at $24.99 and spend $74.97? Why, yes, she could. So she has less than 75 is the total. So less than $25, and she will be able to get 3 pairs of shoes. So the price of the shoes is less than 25. She can't do equal to 25 because it says she has less than 75. But as long as she gets shoes that are less than $25, she is going to be able to get 3 pairs. Write an inequality to represent each situation. Graph the solution. A gym charges $25 per month plus $4 extra to swim in the pool for an hour. If a member only has $45 to spend each month, at most, how many hours can the member swim? Two-part problem here. $25 is a flat rate, so I have $45 to spend, but I have to spend $25 just on the membership fee, which is going to leave me with $20 to spend on the swimming. And it's $4 per hour to swim. 4 times 5 gives me 20 hours. At the most, how many hours? At the most means I include that amount. At the most, the person is going to be able to swim for 5 hours. They can swim less than 5 and they'll be okay. Now, this one has a range. Can you swim less than 0 hours? Well, no, you can't. So 0 is the very least hours the person can swim, and 5 is the most. So it's important we express this as a range. The hours of swimming will be greater than 0, but they could also be equal to 0. But they could also be less than or equal to 5. So the hours swimming are greater than or equal to 0, but they're also less than or equal to 5. How are inequalities different from equations? I hope your brain is screaming at you that inequalities can have lots of possible answers that will make it true. Equations, as we have looked at time and time again, at this point in your math career, equations have one single answer that will make them true. Does the phrase "at most" refer to being less than or greater than something? Give an example to support your answer. At most means that you can have that amount or less than that amount. At most means the most you have, the greatest amount that you have. Everything will be that or less. You cannot go over. My mom says that I can watch at most 3 TV shows after I do my homework. That means that I can watch 3 or fewer than 3 TV shows, but I can't go more than 3. Hopefully you're feeling a little bit better about this infinitely many solutions now that we've put them on number lines and seen what's happening. And hopefully you're feeling okay about writing and graphing inequalities. A big part of this lesson is understanding the vocabulary. What does fewer, at most, less, at least, what do those words mean? We use substitution. We stuck some numbers in to see what makes inequalities true and false. And we wrote and solved inequalities representing real world problems. So that concludes Module 4, Lesson 34. Make sure that you complete your exit ticket. Make sure you complete your problem sets. If you have questions or need help, reach out to your teacher.